In this video I want to explain the basic concepts of vector calculus. And as the name suggests, this is combining two areas of maths that we've now become somewhat familiar with. So vectors, which we've sort of been dealing with for a while, and calculus, which probably a little bit more recently, differentiation, and then most recently just trying some anti-differentiation. So what we're going to do is apply the ideas of calculus, which we know has to do with rates of change, to vectors. And I'm going to make a statement first of all involving a position vector, and we'll use this notation r of t. So a position vector describing the position at some time t, and we'll just use a two-dimensional vector. So let's say it's got an x component or a component in the I direction, which can be described by the function x of t at any time, and a component in the j or vertical direction, which can be described by the function y of t. So x and y are both dependent on t. Well then, using vector calculus, we can say we can actually analyze the rate at which the position is changing, which we know from sort of other studies is really just the velocity, but we can determine the rate at which both components are changing in the same sort of calculation. So I'm going to use the notation r dot t, which you might be familiar with as a notation for the first derivative, but particularly when we're talking about motion, so particularly when it comes to velocity, we use dot notation. So r dot t then is going to be equal to the derivative of r with respect to t. That's just an alternative notation for that. And here we're going to say that we can do that by differentiating each of these components individually. So we can differentiate x with respect to t to get the rate of change in the I direction, and y with respect to t to get the rate of change in the j direction. Or alternatively, we could say x dot t in the I direction and y dot t in the j direction. So they're really just alternate notations for the same thing. Alright, so what we're going to do now is use this idea. Let's actually sort of do an example of this. So let me grab a question from, not from 8a, let's go to 8c. Let's just grab the first question there. So we have a question which is saying find basically the first and the second derivative given these position vectors. So for the first one, we've got r of t being equal e to the ti plus e to the negative t j. So that's the position, and it's asking us to find the first and second derivative, or r dot t and r double dot t. So therefore we know that r dot t is going to be equal to, now I wouldn't normally bother with this, but for the first one let's write down some saying d dt of e of t in the I direction, and d dt. So obviously we're differentiating with respect to t because that's the variable of our function here, our position vector. So we know the derivative of e to the t is just e to the t, so the I component doesn't change. And using the chain rule, the derivative of e to the negative t would be e to the negative t times negative 1, so it would be minus, let me actually get rid of that plus, and just say minus e to the minus tj, and r double dot t, well that's asking us to differentiate again, so let me write out, oops, not j, that should be I, minus the derivative of e to the negative t in the j direction. Once again, the derivative of e to the t is e to the t, so no change in the I component. And here we're going to have take away negative e to the negative t, so it's going to become plus again. So you might notice with that one that its second derivative, r double dot t, is in fact equal to the original position vector. So if this was describing position and velocity and acceleration, then this would be a particle whose acceleration was actually equal to its position for, or at any time. Okay, now that's the basic idea here. Maybe let me do one more with derivatives, and then we'll actually think about antiderivatives, because that's when life becomes a little bit more complex. So let's go the second one here. We've got r of t is equal to ti plus t squared j. So the first derivative, dot t, well, the derivative of t is just 1, isn't it? So it's going to be 1i. And the derivative of t squared is 2t, so it's going to be 2tj. And double dot t, well, the derivative of 1, this is 1i, so the derivative of 1 is 0. So it's going to be 0 times I, which is 0. And the derivative of 2t with respect to t is just 2. So the second derivative there, r double dot t, is 2j. Alright, now there's obviously lots of other types of functions, trig functions, log functions, all sorts of things we might have to differentiate there, but that's the basic idea there. Let's do one that involves anti-differentiation, because these ones are a little bit harder. So I'm going to go down to question 4. And part A, and it's asking us to find r of t given the following. So in this one we're given r dot t, which remember is the first derivative. We're told it's equal to 4i plus 3j, so again just working in 2 dimensions. And we're also given that r of naught, so in other words the position of this object at time 0 is equal to I minus j. Alright, so just think about what that's telling us. It's telling us the first derivative, or the velocity of the particle, could be described by this vector. And we're also given that its position at time 0 is equal to I minus j. And it's asking us to find, let me just write that down, it's asking us to find r of t. So what is the original position? Alright, well, r of t is going to be equal to the integral or antiderivative of r dot t, isn't it? So r dot t is the derivative of r of t, so therefore r of t is the antiderivative or the integral with respect to t of, so that's the integral of 4i plus 3j with respect to t. And just like when we were differentiating, we can do these one component at a time. So basically we're saying if that's the horizontal component of r dot t, or velocity, then we need to integrate, what's the integral of 4 with respect to t? Well, integral of 4 with respect to t is just 4t, isn't it? So that's the I component. Likewise, the integral of 3 with respect to t is just 3t. Now, when we integrate, remember that we need to consider a constant of integration. So we're saying if there was any other constant here, so if I had, something like plus 5i, then when I differentiated this expression here, the derivative of 5i would be 0, and so I'd still just be left with this as the derivative. But importantly, if there was something else like, minus 9j, well, the derivative of that would also be 0. So now when I think about my constant of integration, I need to realize that it could have both an I component and a j component. And there's a couple of ways that I could express that. So one of the ways that I could express that is to go, well, let's say it's, plus c1i and maybe plus c2j. And I think initially that's probably an easier way to understand it. But what we end up doing is, to sort of make life a little bit quicker, is we actually just use the idea of the vector c. So we say the constant of integration is the vector c, understanding that that c could have an I and a j component. Alright, now we're actually given some more information here which is going to allow us to find what that c vector is. So let's state now the bit of information that we were given here, which is that when the time is equal to 0, the position is equal to I minus j. So in other words, What that's saying is, let me write it down here. Remember, this here is r of t. So it's saying when I sub 0 into this expression here, this has to be equal to I minus j. So in other words, I could say 4 times 0i plus 3 times 0j plus c equals I minus j. Now hopefully what we can see from that is that every term that has a factor of t in it is going to be equal to 0 when t is equal to 0. And so what that means is that c is just going to be left equaling I minus j. So therefore down here we could say, well, c, vector c is equal to I minus j. So let's rewrite our vector r of t. Here it is. Let's replace c with I minus j. And so therefore we're going to have that the position vector for t is equal to 4ti plus 3tj plus I minus j. Now we could leave it in that form, or we could, and this will often be a little bit easier to work with, is actually let's collect our I and j components together. So we've got a 4ti plus 1i, don't we? So 4ti plus another 1i down there. So plus 1, that's going to be our I component, plus we've got a 3t and minus 1j. Now I think a sort of helpful thing to do at this stage is, because we're fairly new to anti-differentiating or integrating, is actually to now differentiate this here and just convince yourself that the derivative of this is indeed equal to that, and also that when t is equal to 0, this is just equal to I minus j. So just make sure that it sort of satisfies both of those conditions there.